So, okay, so this video is going to be talking about homework 2 for chemistry module 5. This booklet is about factors of equilibrium. Okay, on the multiple choice, first question, we have that question is asking what information can Lascelles principle provide on a reaction at equilibrium? So choice A says relative concentration of chemical species in the reaction. Well, not necessarily, because so far, Lascelles principle does not have any quantitative basis, so we don't know the concentration. B, changes to relative concentration of a chemical species after a change is imposed on it. Yeah, that's what Lascelles principle is saying, right? It's basically a statement, helps us to predict whether a reaction shifting in which way, given that the system is disturbed by some external source. Okay, so the right answer is B. C, it says like the rates of forward and reverse reactions at equilibrium. Again, does not tell you exactly what the rates are. D, changes to rates of forward and reverse reaction. It does not directly says anything about rate. So anything to do with rates has to come from collision theory, and which is not what we're doing for Lascelles principle. Question 2, a chemical system is at an equilibrium. When heat is added to the system, the equilibrium position will. Okay, so question A says shift to the side with the fewer gas moles. So the chemical system is at an equilibrium when heat is added to the system, the equilibrium position. Right. So no, because fewer gas moles, that's related to pressure. Okay. B, shift to the side with a higher partial pressure of gas. No, again, this is applying to the pressure. C says shift to the left if the forward direction is exothermic, meaning that the reaction is endothermic in the reverse reaction, which is gonna absorb heat. Then by Lascelles principle, increasing temperature, the system will shift such that the temperature is therefore reduced. So going to the left will be the right way if the forward is exothermic. So the choice will be C. Okay. Question 3: what change is responsible for the changing reaction rate at T equals to T naught? So that is this time right here in the graph. So A says increasing concentration of the reactant. Well, that's not, because if you increase in concentration of reactant, this will cause a rapid increase in the forward reaction. But we see a rapid increase for both reactions. So this is not it. Okay. Increasing pressure. Well, increasing pressure does increase the reaction rate for both forward and reverse, but they can be different based on molar ratios, right? Increasing temperature is definitely not in this case, but increasing temperature also changes your reaction rate simultaneously for both forward and reverse. However, one side, if you might recall, the endothermic direction will always be more like increased more. Okay, so the fact that they increase the same amount does not match with B and C. Should be using a catalyst, right? So adding a catalyst decreases the activation energy for like both reactions, and increases the rate the same amount. Okay. Question 4 and 5. So consider the following exothermic reaction. Okay, this is the combination reaction or synthesis reaction of nitrogen dioxide. That's right. So if I recall, the nitrogen dioxide gas is brown, and this reaction written in this way will be endothermic. Which of the following changes would cause N2O4 to be produced? So that if you increase the temperature, the forward direction is endothermic. This is what you guys are supposed to remember. All right. And endothermic, that means if I increase the temperature, the system will shift to the forward direction by Lascelles principle. So you can minimize the temperature change. Okay, so it's D. 5. Which of the following statement correctly describes the initial effect of a decrease in pressure? So a decrease in pressure, system wants to shift so that the pressure is increased back. We believe that system will go in the other way. So the reverse way, you can then produce more gas because there's two gas on the reactant side. Okay. So yeah, the reaction rate will decrease. Well, actually, no. If you sorry. Okay, so Which of the following will describe the initial effects of a decreasing pressure? Well, decreasing pressure will decrease the reaction rate for both reactions. So for reaction rate decreases, but it decreases more than the reaction rate. So as a net result, reaction goes backward. Okay, so it's B. Question 6. The following reaction exists in dynamic equilibrium. Yeah, so which of the following is correct when the pressure of the system is increased? If you have increased the pressure, Le Chatelier principle forces this reaction to minimize that pressure increase. Therefore, you want to shift to a direction to have a lower gas moles present, which is the forward direction that's being favored. Okay, which means that we're going to increase the yield of NOCl2. Okay, that's what the selection B is saying. Okay, right. Question 7. The Haber process involves the synthesis of ammonia, NH3, from nitrogen gas and hydrogen gas. So the reaction goes as this, it's exothermic forward. What will be the effect of a decreasing pressure? So if you decrease pressure, reaction will shift to the direction where you produce more gas to increase pressure back. Okay, which means it goes to the reverse direction, and that corresponding to endothermic pathway, which means heat will be absorbed. Okay, just as a consequence of shifting to the back. Right, it's pretty trivial. I mean, if my students have any confusion on like why is like other choices wrong, I won't go like in much detail in this video. But if you guys have a question, please just ask me, give me a question on WeChat, whatever. Okay. So reaction between ion 3 and thiocyanate ion forms this little equilibrium. Okay, and this question applies to H210. So which of the following action will cause the solution to become more blood red? If you might recall, this ion is actually the blood red complex. Okay. Yeah, so A is wrong because pressure does not apply to aqueous system, so that's just out of the way. B is wrong because add a fluid droplet concentrated Ag. Yeah, so Ag which will actually form precipitate with this, which decreases the concentration of that. So in fact changes the concentration of that, and then the reaction shifts this way. Okay, so that's not good because we want to produce more of this to make it more blood red, right? So the right answer will be C, because if you add KSCN, potassium thiocyanate salt, this will dissolve and it will further increase the concentration of that. And therefore, by Le Chatelier principle, system shift to the right. Therefore, you reduce the concentration of that, but you end up producing more of this blood red complex. So C is the right answer. Question 9. What will be the effect of diluting the solution? So if you dilute the solution with the distilled water, everything concentration just decrease. Okay. Since now we have two aqueous substances on the reactant, so the changing concentration is much more significant to the reactant, right? Since we have diluted the solution, okay, concentration has decreased, so we want to shift in a way such that the concentration is increased. Therefore, equilibrium will shift to the reverse direction, so the reduction in those two concentrations is decreased. Okay, all right, so it's actually D. So it says the equilibrium position shift to the left to produce more of that. Okay, good. Question 10, when the solution is heated, the intensity of the blood red color will decrease. Which of the following can be inferred about this observation? Okay, so this reaction, the forward reaction is exothermic, right? So if you heat the solution, okay, you get less blood red. That means if you heat the solution, everything goes back. Right? You reduce the concentration of that. Okay, that means so temperature is increased. That means shifting this way must decrease the temperature by Le Chatelier principle, which means shifting this way has a delta H that's larger than 0. Okay, which also means that going this way has a delta H of smaller than 0. That means the forward reaction is exothermic. Okay, so B is the right answer. Okay, extended response, question 11. Pretty much just the definition of Le Chatelier principle. Copy straight away from my notes or write it one for yourself. As long as it makes sense, it should be fine. Okay, so let's read mine. So it's a statement that allows the prediction of equilibrium shift. okay, when the system is disturbed. It states that the system at dynamic equilibrium will shift to counteract any initial change and eventually re-establishes equilibrium. Question B, explain what is meant by equilibrium position. So equilibrium position is a specific state of dynamic equilibrium. It quantifies basically like the concentration ratio between products and reactants. Yeah, so that's what it is, okay? Equilibrium position can of course be changed given that you have the three factors of equilibrium, okay? Question 12. Question 12, a solution of cobalt chloride ion exists in both hydrated and dehydrated form. The following is the chemical reaction. Question A says you use collision theory, so this is last week's stuff. I mean, technically, last lesson stuff, lesson one stuff. Explain the effect on the solution's color. If a few droplets of concentrated sodium chloride was added. Okay, yeah. So the introduction of sodium chloride, okay, sodium chloride will therefore dissolve, right? And that increases the concentration of chloride ion in the solution, which means by Le Chatelier's principle, system will shift forward, trying to decrease the concentration of the chloride ion. Okay, remember that for these questions, you must define Le Chatelier's principle. Okay, if I was marking your answer, if you didn't define it, I'll take off a mark. Okay, if you are marking this yourself, okay, be honest, take off a mark. Okay, so if you it's by collision theory. Okay, oh, by the way, okay, my bad. So this part A is actually talking about collision theory instead of a Chatelier's principle. I guess that's for part B. Okay, yeah. So emphasis, read the question carefully. Okay, yeah. So in terms of collision theory, increasing concentration increases the number of collision and therefore successful collision. Yeah, or you have to mention all that, and therefore increase the reaction rate because of that. So the forward reaction will be favored because forward rate is now higher. Right, nice. And question B, predict the effect of adding water to the solution justified with Le Chatelier's principle. Very good. So adding water to the system, okay, it doesn't have a concentration for water. Water is a it's part of this reaction. Okay, it's a product. But adding water does not increase something called the concentration of water. It doesn't even exist. Right? Water is liquid, no concentration for that. But adding water changes, like indirectly changes the concentration of these because you're diluting the solution. Okay. Now, since I have two aqueous substances, only one aqueous substance on the right hand side, that means diluting the solution will make the concentration of these like much more significantly smaller. Okay. By Le Chatelier's principle, we want to shift so that this change is minimized. So we must go to the left. Okay. So adding water into the system, although it doesn't change the concentration, it still dilutes the concentration of other reagents. Okay, since there are 5 molar, is it 5 molar of reactants? Yeah. Okay, sorry, man. This is 4. So in total, it's 5. Okay, not 2, 5. Okay, so it's 5 molar of reactants versus 1 molar of product on the right hand side, so that the reduced in concentration is more significant for reactant. Therefore, by Le Chatelier's principle, the equilibrium will therefore shift to counteract initial change. In this case, okay, this is me defining. Okay, this is me defining LCP, and then this is me address the question. Okay, so that's the sample answer. Let me check if I recorded this or not. Yes, I did. Okay. Look, if you have no idea how to write these questions, that means it's time for you to ask. Okay, it's very important for you to understand how to answer these questions. Super important. Question 12 continued, part C. Okay, so this one's a bit more challenging. So solutions of sodium nitrate, sodium chloride, and calcium chloride, they have equal concentration but are mistakenly labeled. So you have 3 bottles of them, and then it's like you don't know what they are. Okay. Explain how a cobalt chloride solution, yeah, which is the equilibrium given here, right? You explain how that can be used to identify these 3 solutions. Okay. So first of all, we can basically add cobalt chloride into like these 3 bottles of them. Okay. So this is what I do. So introduction of cobalt chloride ion forms that equilibrium. Okay, and the equilibrium react will they're going to react differently with like when these things are present. Okay, so this is a very clear sign that you can use a dot point to answer. Okay, so the first dot point will be on that. So, well, sodium nitrate in a solution will dissociate into ions. Okay, like that. Okay, so both sodium and nitrate ion, they are called spectator ions for the cobalt chloride equilibrium. Like they are not present in this equilibrium, so it doesn't really matter if it's there or not. Okay, they're spectating. So as a result, there's going to be nothing's gonna change. You basically is equivalent as adding 9 to water. Okay, so for sodium nitrate, nothing's going to change. No significant effect. However, for sodium chloride, you can see how it dissociates into chloride ion. Okay, now chloride ion from sodium chloride is actually going to interfere with the chloride ion in this reaction. Okay, how does it do it? It increases its concentration. Okay, and then we can use the Le Chatelet principle. Therefore, it's going to shift to the right. Okay, so formally, we can just write this equation, and then the chloride ion, when mixed with that, increases the concentration of that. Therefore, by LCP, equilibrium shift to minimize the concentration of that. Therefore, shift right in this case. Okay, so because of that, the system will actually turn blue. So the solution turning blue is like a thing that you can use to distinguish whether it's sodium chloride or not. Okay, so it's very important for you to mention that this color change and what color is changed to, for you to justify yourself that we can actually identify it. Okay. Another thing is that you need to know that this is blue, this is pink. Okay. And then the last one is like calcium chloride. Okay, so calcium chloride dissociate like this. So you see how it produced 2 chloride ions instead of 1 above. So this is very similar compared to sodium chloride. It's still gonna increase the concentration of chloride ions, still gonna shift forward. It's still gonna turn blue. However, because we have 2 chloride ions, that means we're increasing more chloride ions than for the case of sodium chloride, which means that the equilibrium will shift more significantly, which means that the color will be more significantly appeared. Okay. So yeah, that also distinguishes calcium chloride with sodium chloride because the color will be more intense for calcium chloride. Okay. Yeah. So out of the 3 solutions, sodium nitrate does not have anything happen, no color change, just a mixture of pink and blue, probably purple. Okay. Sodium chloride will turn blue. Calcium chloride will turn very blue. Okay, so that's basically what you can see as an observation. Okay. Question 13. A solution of iron thiocyanate ion. Okay, this complex exists. We've seen this a few times. Okay. Ask you to define what is the dynamic equilibrium. Okay, very trivial question. So it's basically a state of reversible reaction where both forward and reverse reaction rates are equal but not zero. Okay. Question B, outline 2 ways that the solution can be made to have a much more blood red color. Just like your answer with the Le Chatelet principle. Guys, this question is very easy. So one way is like try to talk about 2 different factors of equilibrium. There are 3, right? Concentration, pressure, and temperature. Although that this reaction only involves aqueous conditions, so no pressure, right? Pressure doesn't apply here, but you can mention concentration and pressure and temperature. Okay, don't just say like, okay, you can increase the concentration of Fe3 plus, and you can also increase the concentration of SCN. If you wrote that, you're correct. I would mark you correct. Okay, or you can say you decrease the concentration of the. Oh no, actually you can't, because like if you say you decrease the concentration of Fe SCN, reaction shift forward, but since you have decreased it in the first place, it's gonna shift forward to minimize that change, but it's not gonna minimize that much. Okay, so it's still gonna end up getting less blood red. Does that make sense? Okay, so you must say something like increase the concentration of the reactants. Okay, and you could also mention temperature. Okay, so I'm just gonna pause here for like 2 seconds for you to, if you need to like copy the answer. If you made a mistake, just freeze the screen. Let's just pause the video. Okay, I'm not gonna go through this. It's too easy. Okay, same drill. Define the Le Chatelet principle. Yada yada yada. Okay. Question C. So question C gives you an energy profile diagram. So as you can see, this is like an exothermic direction. Okay, if you don't know how we can determine it's exothermic or endothermic from this diagram only, you need to revise on your energy profile diagram. So definitely let me know about it. Okay. But yeah, for students that can recognize this as exothermic direction, exothermic reaction, we can use collision theory and talk about it. So this is just you have to use the Maxwell-Boltzmann distribution to try to justify it. It's like a larger portion of change in endothermic pathways. Okay, so let's use collision theory to explain. So increasing temperature of the system will actually increase the average kinetic energy of the system. Okay, so that the distribution of particle energy will shift as follow. Okay, so as we discussed in class, it was actually lesson 1. So a lower temperature gives you that Maxwell-Boltzmann distribution. A larger temperature gives you a flatter one. All right, so that the area under the curve is like number of particles at that energy is increased because of temperature increase. Okay, so observe that the energy profile, activation energy for the reverse reaction, right, which is that, is going to be higher. It's not much higher, but it's higher. Okay, so I should use a different word here, but it's fine. Than the forward. So the effect of increasing temperature is hence more significant for the reverse endothermic direction. This is because that the portion of particle increase is greater. Now I'll just talk about that again. So this is the reverse, which is endothermic. Initially it has this much, but then increasing temperature you have this much. So you sort of like increasing more portion. In contrast to your forward reaction that's exothermic, because it has a smaller activation initially, it has a lot of particle that can undergo successful collision, right? But then you increase the temperature, yeah, sure, area increased, but the portion of increase is less. Okay? Therefore, changing temperature has a more significant effect on endothermic reaction. Okay, so this is like a sample answer for you to write about collision theory and justify temperature change. As a result, the reverse reaction rate overcomes the forward reaction rate. Therefore, the reaction actually goes to the reverse direction. Okay, and don't forget, okay, you can also talk about the color change as well. Okay, but that's fine. Question 14. So again, the nitrogen dioxide example. Now this equilibrium was placed inside a vessel which we can change its volume and hence pressure. Okay. Why is the gas syringe, okay, a closed chemical system? Because nothing can escape. That's basically the definition. But energy can also exchange. Okay. Using collision theory, identify and explain the observation that would be made when the plunger is pushed. Okay. Make sure you mention color change. Okay. So when the plunger is pushed, the volume of the system is reduced, causing partial pressures of nitrogen dioxide and dinitrogen tetroxide to increase, and therefore more frequent collision plus successful collision. This must be mentioned every time for collision theory. As a result, rates for both forward and reverse will therefore increase. Okay, due to molar ratio, the effect of rate increase is more significant for forward reaction, so that the equilibrium shifts forward. Okay, yeah, and then the color changes from like brown to colorless. You have to remember the color as well. Okay, these questions are pretty standard. Question 14C. When the syringe is placed in a beaker filled with cold water, the mixture becomes darker brown. Darker brown means like basically concentration of NO2 has increased. Determine whether the formation of that is endothermic or exothermic. Okay, so like we said, darker brown indicates more NO2, which means reaction shift to the left. Okay, so what's the change here? So identifying the change is like cold water, which means temperature decrease. So that's the change. So temperature is decreased. This is the change, and it causes reaction to shift left. Cause that, right? But then this cause by Le Chatelier principle is trying to minimize this temperature decrease. That means so that this cause is exothermic to do so. Okay, so reverse is exothermic, forward will be endothermic. Okay, so as the mixture turns brown, when temperature decreases, that means that the equilibrium shifts to the left. By LCP, equilibrium will overcome this initial change. Actually, no. I'm gonna correct myself. It's not gonna be overcoming. It's going to be minimizing. Okay, it never minimizes like more than that you changed for. Okay, it never does that. Okay, minimize. Uh, minimize. Okay, so hence the reverse reaction, okay, must be exothermic. So conversely, the forward reaction is endothermic. Okay. Question 15. Chlorine dioxide. So this is again an ionic compound. Oh no, my bad. This is a covalent compound. Okay, to nonmetals. It is highly reactive oxidant. Okay, so that means it reduces itself, oxides the other. Revise module 3 if you don't know what I'm talking about. Yeah, that is used as a disinfectant in pools. Okay, it can be produced from chlorine gas and oxygen gas, and then the reaction reaches equilibrium in a closed system. Okay, balance equation will be something like this. All right, literally just tells you the equation in Word. Okay, so just translate that. I know you have never seen this before, but you can translate from the question. And this is going to be happening in HSC. Like they're just gonna give you something that you never seen before, with the hope that you actually can be able to write it down using your general chemical knowledge and your common sense. B. What can you conclude about the reactions Gibbs free energy delta G? Justify your answer. Well, if I have a look at that, I mean, this is a pretty equilibrium reaction, right? So it also says that it reaches equilibrium in a closed system. Again, it says if it reaches equilibrium, by default, that's dynamic equilibrium, which means that if the system is at dynamic equilibrium, that means there's no macroscopic change. It's by definition. Therefore, the Gibbs energy is a macroscopic property, so it's going to be changing zero. Okay. Yeah, titration no, oh, sorry, my bad. No, titration curves. I just finished a lesson with my year 12 students, so um, doing HSC, so it's kind of making mistakes right now. Right, this is concentration curves, okay? So it gives you some information and asks you to draw the curve. So at T1, the pressure is increased. So like we discussed in class, pressure increase is caused by volume, and that will change the concentration of everything simultaneously. And that's why we have a like everything just increases, like a sharp increase, okay, indicated by T1 here. And then at T2, some amount of chlorine gas is removed. That's why this is a big change. T3, small quantity of oxygen gas is pumped into the system. Okay, and then so at T3, small quantity of oxygen gas is pumped into the system. Did I make a mistake here for this question? Okay. I think I actually did. Yeah, because this should be like an increasing oxygen. I'll fix that later. Okay. So but like the question is just like, okay, I'll actually draw it right now. It's like, why not? Uh, I'm just gonna correct that with this. A small quantity of oxygen is pumped into the system. How can I make this mistake? What the hell? So oxygen now is pumped into the, what the hell? This should be black. Okay, that's nice. I'm gonna redraw this diagram. Okay, so oxygen is pumped into the system, small quantity. Let's say that. Okay, so now that the reaction will actually shift forward. Okay, yes, it will shift forward and produce a little bit of the chlorine. Sorry, consumes the chlorine gas. So chlorine will actually decrease by 1. Let's try to do that. Okay, and then oxygen will decrease by 2 because of the molar ratio. Okay, it'll be decreasing. No, no, decrease by 2. Okay. As a result, that thing will also increase by 2. So roughly symmetrical, and we eventually reestablish equilibrium. Okay. Right. So yeah, that was a bit of mistake, but here, there you go. Now during these like gradual changes, just use the Charlie principle, figure out which way it's going to change. Okay. One thing is very important to focus on is roughly the proportionality. Okay, because of the molar ratio. Make sure you have that. And if you're not sure, you can give it. Let me have a look of your answer. Question 16. Sulfur trioxide can be industrially produced from reacting sulfur dioxide and oxygen in a closed system. Typically, a high pressure setting and excess oxygen are used to optimize the equilibrium yield and rate of the sulfur trioxide. So this process, if you don't know it, it's called the contact process. We'll get to learn more about this in module 8. So the equilibrium yield of a compound refers to, okay, this is just explain what yield means. It's pretty straightforward. It just means how much you produce, right? Right, A, use the Shelly principle, justify the use of setting outlined above, include a chemical reaction. LCP definition, right? Yada, 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 changes will be counteracted. And then you write this equilibrium down, okay? So in this case, if you have a high pressure setting, okay, this actually shifts forward, so which maximizes your yield, as well as the rates, right? Because increasing pressure increases the rate of reaction too. This is very nice. But then you can also use excess oxygen. Okay, so excess oxygen is kind of free, just in the air, right? So you don't need to, if you're the company, if you're the boss of the company, you don't need to like have a lot of cost to use oxygen, right? So use excess oxygen to shift the equilibrium forward, and which that reduces the oxygen concentration to as supposed to be minimizing its concentration due to the shift. Okay. Right. So and students gonna ask like maybe that's part B. Let's talk about it. Okay. So the graph shows like this like a pressure and gradient, sorry, and a temperature graph, right? So these like level curves of different pressures. Different temperatures, and then the x-axis is pressure, y-axis is the yield. Okay, so the aim is like I want this as high as possible. Okay, I want this as high as possible. So yeah, the industrial production of sulfur trioxide occurs at 450. So this one. Okay, despite that the yield being greater at lower temperature. See, like this one has a larger yield, right? At some given pressure, it has a larger yield, right? So why don't we just choose 350 instead of we actually choose 450? So the idea here is like, I mean, we could choose 350 and get more yield out of it, but simultaneously, this occurs at a smaller temperature because the whole reaction is like exothermic, right? So that lower temperature gives you more yield. It shifts forward to just absorb to produce more energy from exothermic reaction. But simultaneously, reducing that temperature will reduce your rate. Okay, so yeah, you do have a larger yield, but it's probably going to take a while for you to get that, and that's not going to be efficient. Like imagine if you're running the company, and then like you have to wait for a month to like get a shipment ready, right? It's not quite efficient. You're not gonna get much from it. Okay, so instead we actually want some rate out of it as well. Therefore, we sort of don't need that much like small temperature. We sacrifice a little bit of the yield, but we get the rate boost up. Okay, we try to maximize our rate with temperature, and then with other stuff, we try to maximize our yield with other stuff, such as pressure. Okay, we want to have a larger pressure as possible, a larger like concentration of the reactant as possible, so that we get this yield maximized. But for temperature, we somehow can't do that because if the temperature is low, we don't have any rates. But if temperature is high, we don't have any yield. Okay, so this is called a rate yield conflict. Okay, and then scientists trying to choose the optimized temperature. Okay, which is happens to be 450 in this case. Like scientists must work it out, right? So to explain that, he just talk about how temperature affects the reaction rates, the collision theory, right? Yeah, okay. So it's the same drill. Let's read it. So the production of sulfur trioxide is exothermic reaction, meaning that for lower temperature, reaction rate is suppressed for both forward and reverse reactions. So endothermic direction is reduced more than the exothermic direction. So you can basically say that you don't need to always draw that diagram. Okay, it depends on like the question. This question is more focused on: are you able to understand? Do you really understand what's going on, rather than like demonstrate what collision theory really is and the curve and stuff, okay? So as a result, reaction will shift forward and the equilibrium yield, okay, for SO3 is entire. Okay? So this is not implemented because low temperature forces the rate to be very slow, okay? So for a more efficient reaction, temperature is kept relatively high and pressure is selected to be large, okay, in order to favor your reaction yield, okay? So we don't get yield from temperature. We get rate from temperature, and we get yield from other like sources. Okay. Okay. So this week's challenging question is a bit of physicsy. Okay. So it's like a statement. Okay. So if you do physics, okay, I think this is a misspelled word. It's a chemical. Okay. It should be chemical, but that's fine. Let's pretend that doesn't exist. So use chemical equation and examples to discuss the relevancy of Le principle to Newton's third law. Okay, Newton's third law states that every force of action corresponds to an equal but opposite reaction force. If you do chemistry, you might not know this. If you do study physics with me as well, you should know this. Okay, if you don't know this, let me know, and I'll have a hard time on you. Okay. Yeah, like how is this related to Le principle? This is like a deeper understanding. Okay, so our universe, I don't know if you noticed this or not, but it's far. Okay, uh, runs on a bunch of symmetries and conservations. Okay, right, and Le principle is nothing but really just a conservation of energy. Okay, and same thing as Newton's third law. Okay, so they just eventually just lines up, right? It's conservation. Okay, so yeah, like in Le principle, the opposing effect is kind of like the opposing force from Newton's third law. It's basically the same. We have this because energy must conserve. Like anything that any changes to any system has a consequence, and that consequence always try to minimize this change. So that is kind of like this conservation. Okay. So I started with an example. For example, the conversion of that into that, this reaction, LCP states that the system shifts so that the external change is minimized. So this is analogous to Newton's third law, as in like say, if this increase, the equilibrium will shift to the right so that this is decrease. Is basically an analogy to like a hand that's pushing a box, and then the box is also pushing back on you, on the hand, so that the hand is feeling a reverse force, trying to like stop the hand from pushing the box. Okay, does that make sense? It's kind of like this opposing effect. Okay. Also, I'll let you think about this. All right. So yeah, this will be it for this week's homework. All right. So enjoy chemistry. I'll see you next time.